Okay, here we are with the second question. We've got a bit of deja vu. So, two astronauts, Sylvia and Sam, are on a mission to another planet. During their journey, they're doing a spacewalk outside their spaceship. At one time, they are moving freely as shown on the diagram below. They collide and stick together. Hate it when that happens. Calculate the distance between Sam and the centre of mass of the system when he and Sylvia are 4.80 metres apart. Alright, so we're going to use the same equation again, and the question states that we need to have the distance in relation to Sam. So I'm going to use Sam again as the point that I'm measuring all of my distances from. So I'm going to put Sam in this position here. The position of Sam in relation to Sam is 0. Sam's mass is 105 kgs. Then the position of Sylvia in relation to Sam is what the question states. So it says that they're 4.80 metres apart. Then the mass of Sylvia, 95.0 kgs, divided by the total mass of the system, which is 105 plus 95 kgs. Slap all that into the calculator. I'm not going to do this first part because it's multiplying by 0, so I know it's going to be 0. I'm just going to do this second part here. 4.8 times 95. Divide that by the total mass of the system, and we get 2.28 metres from Sam toward Sylvia. So like the last question, the distance of the centre of mass from Sam is going to be along a line directly from Sam towards Sylvia, and it's going to be 2.28 metres along that line, which is slightly less than half of this distance, which is what you'd expect since Sam has slightly more mass than Sylvia, but not much more. So after that little check, I'm going to move on to the next question, which is a description. So I'll probably just do that verbally. Describe what happens to the centre of mass of the system as the astronauts move closer together and then they collide. Well, you can kind of imagine it like this. If this is the position of Sam before the collision, and this is the position of Sylvia before the collision, and this is their position when the collision happens, and then some point later in time after the collision, bang, boom, crash happens here. So Sam is going to move to this position here, Sylvia is going to move to this position here, the collision takes place and they travel off together in this direction here, stuck together. The dotted red line is where the centre of mass is going to travel. Okay, so this is the centre of mass at the start, yeah, and then that's going to go at a constant velocity. And it does ask me to justify why. Describe what happens to the centre of mass of the system as the astronauts move closer together and then collide. So I'm going to say because there's no external forces acting, the centre of mass will travel at a constant velocity. So we calculated in the previous question where the centre of mass would be between them. At the position of when they collide, the centre of mass is going to be between both of them, and then they're going to move off in the direction that the centre of mass was travelling before the collision. Okay. Then question 3, calculate the astronauts' combined speed after they collide. So this again is going to be a conservation of momentum question. You can do an interesting thing with this previous equation up here. So this is 1c. We can take both sides of the equation and divide it by t. Because if we take a distance or a displacement here and we divide by t, we've got a velocity, and this is going to be the velocity of the centre of mass. Okay, and they are going to be moving with the centre of mass after the collision. So this is actually going to be our answer here, but that means I need to divide this whole side by t as well. So write it down like this to start with so you can see what I'm doing. So I'm going to take all this and I'm going to divide it by t, and that's like putting t on the bottom line here, and then all I'm going to do is take my t and divide each of these values here by t. Okay, so if I get x1 over t times m1, and I get x2 over t times m2, so I'm just taking this t, dividing the x values by t, and then leave these here. These are also speeds. Okay, so we get v1 m1 plus v2 m2 over m1 m2, and I'm going to simplify this down here to v centre of mass. V centre of mass. Okay, so what we've done here, if you look at this, I've changed the centre of mass equation into ones with velocities and masses multiplying together, and we know that the velocity times mass is the momentum. So if you find the total momentum of the objects in the system, which is this top line, divided by the total mass of the system, you end up with the velocity of the centre of mass. Bumblebee's just flown in here. What do you want? I'm just going to pause the video till the bumblebee goes away. And the bumblebee's gone. Right, so now all I need to do is substitute some values in here and I'll have the answer that I need. So, or will I? Almost made the fatal mistake of considering these as if they were scalars. So I need to add these together as if they were vectors. This is exactly like the previous question. So let's have a look at what that looks like. We've got Sam coming down here, and Sam's momentum is Sam's mass times Sam's velocity. Why did I write it like that? Really haven't left myself much space, have I? Which is 105 times 1.20. Stick these into the calculator. 105 times 1.2 equals 126 kg meters per second. We're going to add to that the momentum of Sylvia, P S Y P psi equals mass times velocity, and the mass of Sylvia is 95 and her velocity is 1.4. She's really macking along. So that means we get 95 times 1.4 equals 133 kg meters per second. So now we can find the total momentum of the system. Remember, the total is always from the first tail to the last head. So P total is equal to, in this case, the square root of P Sam plus P psi squared, both squared. 126 squared plus 133 squared. Plug that into my calculator. Really should lay out my paper a bit better. Haven't really left myself much space. Cool, and we get 183 kgs meters per second to three significant figures. Okay, so that's the momentum, which is the total momentum of the system, which is effectively working out the top line of this equation here, but I needed to add them together as vectors, which is why I had to use Pythagoras over here. Right, so now I can do the final part, which is divide this total momentum by the total mass. So I'm going to put 183 in here, and then divide that by the total mass of the system, which is the mass of Sam and the mass of Sylvia. Cool. So my calculator has still got the same answer in it, so I'm just going to divide that by 105 plus 95 in brackets, and I get 0.916 meters per second, and that's the three significant figures. Cool, so that's their combined speed after the collision, because this is the speed of the centre of mass, and after the collision they are moving off with the centre of mass. Cool, so I'll move on to the next question now.